Hi guys, when we finished class, we were just starting to talk about clouds and how they form by water vapor condensing out of air that has been lifted and cooled. About 4 distinct mechanisms through which air can be lifted. One is through the convergence of air masses, another is through surface heating, then we have orographic uplift around mountain ranges, and then finally frontal lifting. In the next few slides, I'm going to show you a few photographs of the different types of clouds. We'll note which clouds in particular are important for climate, and then finally in this little mini lecture video, we'll talk about why those types of clouds are important for climate and how they're important for climate. So clouds formed by orographic lifting typically look a little bit like this. You could kind of see the outline of the mountain range here. Other times they could form rolling-like structures. You could often get these lenticular clouds, which look like lenses. These form over particularly high and cold mountain ranges. And I'm not going to make you responsible for identifying different types of clouds. This is more for your general interest. But the types of clouds are classified as stratus or nimbostratus, stratocumulus. We have lenticular clouds, cumulus clouds, sometimes cumulonimbus clouds. These all tend to be fairly low in the atmosphere. At middle layers, we get clouds like these cotton ball type structured altocumulus clouds. We get altostratus clouds. Stratus clouds tend to form this uniform mass. They're fairly featureless. And then finally, at the highest levels, you get clouds that are a mixture of ice crystals and water vapor. You have cirrocumulus, cirrostratus, and cirrus clouds. So here's a few more photographs. We usually associate cumulonimbus clouds with dark, massive thunderstorms. These form in places where you get convective lifting of air. They tend to produce fairly explosive showers, a lot of thunder and light. Here's a photograph of cirrus clouds. These are high clouds. High clouds, like cirrus clouds, have important implications for climate. And in a few more slides, we'll talk about exactly what those are. Typically, these types of high clouds that are fairly loosely packed, like the cirrus clouds, are thought to have a warming effect on climate. Over here, we have altocumulus clouds. These are the clouds that look a little bit like patches of cotton balls. Sometimes you see them arranged in lines or groups. Sometimes you get them in the form of rippling waves. But they're the clouds that look a lot like cotton balls. Stratus clouds are another type of cloud that are particularly important for climate. These are clouds that tend to be at fairly low altitudes. They're relatively featureless. They're uniform. We see a lot of these off of California. It's quite common that stratus and stratocumulus clouds will come in off the ocean in the form of these large cloud decks, like the one that you could see here off the coast of Southern California and Mexico. So finally, to get you guys prepared for next week's lab, I'm going to talk a little bit more about clouds and the global energy balance, and then in class on Tuesday we'll talk about, in more specific detail, about the feedbacks that clouds are involved. So just as a reminder, clouds do cover a large fraction of the Earth. This is another view of the Earth looking from space. One of the things that you'll recall is that Earth's albedo is about 0.3, and this is largely as a result of the brightening effects of clouds. Earth's albedo would be a lot lower were it not for clouds covering a large fraction of the Earth's surface. So clouds are actually a really difficult thing to include in climate models because they have opposing effects on climate depending on what type of clouds form and what their density is and what their altitude is. So the opposing effects that clouds have are that they reflect sunlight. So this is a cooling effect on climate. You might think of this as a negative effect on climate. Clouds also absorb and re-emit long-wave radiation, which is a warming effect. You could think of the clouds themselves as black bodies. And as you know, black bodies will absorb long-wave radiation that's emitted from the Earth and then emit it upwards into space and downwards into back to the Earth's surface. And so that is a warming effect or a positive effect on climate. These two opposing effects are also why we typically find cloudy days to be fairly cool, but cloudy nights to be pretty warm. Cloudy nights are warm because the clouds themselves are sending a lot of the heat that they absorbed back to the Earth's surface. Cloudy days are cold because the primary thing that we notice there is that the clouds are blocking a lot of incoming shortwave radiation and sending it right back out to space. But over long time scales and over changes in cloud cover that we would expect with changes in climate, which of these two effects wins out? This has been the topic of a lot of debate in science. I'm not going to get into the nitty-gritty, but in a nutshell, it's important to keep in mind that thin high clouds tend to warm the climate, whereas thick low clouds tend to cool the climate. So we'll talk a little bit about what this is. The reason why thin clouds tend to warm the climate is that thin clouds do let some sunlight through. They're pretty bad at blocking incoming shortwave radiation, whereas thick clouds reflect the most sunlight. So in order to understand whether clouds have a net cooling effect or a net warming effect, we have to think about the fact that a lot of times the clouds that form at high altitudes are fairly thin, whereas the clouds that form at low altitudes are pretty thick. So these high thin clouds will end up letting a lot of incoming solar radiation through. I'm going to go ahead and draw that here. So they let shortwave radiation through. And the clouds that are located lower and are thicker are more effective at reflecting incoming shortwave radiation back to space. So let's now, I did not mean to do that. Let's now think about what happens with the long-wave radiation. So this is the radiation specifically that's re-emitted from the Earth through the process of blackbody radiation. Well, both the high thin clouds and the low thick clouds are going to effectively absorb this long-wave radiation and re-radiate it back to Earth. So it turns out that when you have a lot of high thin clouds, those clouds are letting a lot of shortwave radiation through. They're also absorbing a lot of the long-wave radiation. I'm just going to draw that with some orange lines here. So this is, let me revise that. Here we go. I was trying to draw orange for you guys, but it's not letting me do that so easily. Okay, let's try this. There we go. So the long-wave radiation is getting absorbed by these clouds and then reflected back to Earth, reflected back into space. Low thick clouds are also absorbing long-wave radiation and sending it back to Earth and into outer space. Now, the thing to think about is which of these processes dominates. And for the high thin clouds, there's a lot of shortwave radiation getting through. There's also long-wave radiation coming back down to Earth. The long-wave radiation is what wins out here. And so high thin clouds end up having a net warming effect. Whereas for the low thick clouds, the process that really wins out is the reflecting back into outer space of the shortwave radiation. So this is really what wins out, and these low thick clouds end up having a cooling effect. So this summarizes those ideas. Thin high clouds warm, low thick clouds tend to cool. And basically the reasons that I just verbally went through are listed here. So then the big conundrum for climate scientists becomes a question of whether increased temperatures are going to add to the global coverage of these low thick clouds preferentially or the high thin clouds preferentially, and that's what there's a lot of disagreement about right now. You're going to deal with some of the most recent findings in your lab next week when you're going to take a look at a paper that just came out that talks about how climate warming is predicted to change the abundance of a particular type of cloud. And then you'll have to think about that in the context of what I'm presenting here to figure out whether and why that has a net cooling effect or a net warming effect. So that's all I wanted to go through today. In class, we'll talk in more detail about the role of water in global warming feedbacks, and we'll do that as an interactive discussion. So make sure you're there. Okay, see you guys next week.